Achieving specific sound transmission class, or STC, ratings in wall construction requires careful consideration of stud spacing. The International Building Code and standards set by the American Society for Testing and Materials, specifically ASTM 90, outline the testing procedures and requirements for determining STC values. These standards are crucial in ensuring that wall assemblies meet the desired acoustic performance. An STC rating is a single number rating of a material's or assembly's ability to resist airborne sound transfer at frequencies of 125 Hz to 4000 Hz. A higher STC rating indicates better sound isolation. The testing methodology described in ASTM 90 involves measuring sound transmission through a wall assembly that is 8 feet wide and 9 feet tall. A key aspect of this test setup is the stud spacing, which is specified at 16 inches on center, often abbreviated as OC. This means that the distance from the center of one stud to the center of the next stud is 16 inches. The STC value obtained from this test configuration serves as a benchmark for assessing the sound isolation capabilities of the wall assembly. If the goal is to achieve an STC rating in the range of 45 to 49, adhering to a stud spacing of 16 inches OC might not be sufficient, especially if other elements of the wall assembly are not optimized for sound isolation. In many cases, to reach an STC of 45 to 49, the studs should be spaced closer together, typically no more than 12 inches OC. This tighter spacing provides additional support and reduces the potential for sound vibrations to pass through the wall. Similarly, for applications requiring a higher STC rating, such as 50 to 56, even closer stud spacing is necessary. To achieve this level of sound isolation, the stud should be spaced no more than 10 inches OC. This further minimizes sound transmission and enhances the overall acoustic performance of the wall. Going every other stud, which would result in a stud spacing of 32 inches OC, would be inadequate to achieve the desired STC ratings of 45 to 49 or 50 to 56. The increased spacing would significantly compromise the wall's ability to block sound, leading to lower STC values. Several factors contribute to the relationship between stud spacing and STC ratings. Firstly, closer stud spacing increases the stiffness and mass of the wall assembly. This added stiffness reduces the amplitude of vibrations caused by sound waves by minimizing sound transmission. Secondly, tighter stud spacing can improve the performance of insulation materials placed within the wall cavity. When studs are spaced closer together, the insulation is more effectively compressed, which helps to dampen sound vibrations. Thirdly, the type of material used for the studs also plays a role. Wood studs, for instance, have different acoustic properties compared to metal studs. Wood studs generally provide better sound isolation due to their inherent damping characteristics. In addition to stud spacing, other elements of the wall assembly can influence STC ratings. These include the type and thickness of the drywall, the use of resilient channels, and the presence of insulation. Firstly, using thicker drywall, such as 5/8-inch drywall, can significantly improve STC ratings compared to thinner drywall, such as 1/2-inch drywall. The increased mass of the thicker drywall helps to block sound transmission. Secondly, resilient channels are metal strips that are attached to the studs and used to mount the drywall. These channels create a decoupling effect, which reduces the transfer of vibrations from the studs to the drywall, thereby improving sound isolation. Thirdly, filling the wall cavity with insulation, such as fiberglass or mineral wool, can also enhance STC ratings. Insulation helps to absorb sound vibrations and reduce resonance within the wall cavity. To optimize STC ratings, a comprehensive approach that considers all aspects of the wall assembly is necessary. This includes selecting appropriate stud spacing, using high-quality drywall, incorporating resilient channels, and filling the wall cavity with insulation. Consulting with an acoustical engineer or contractor can provide valuable insights and recommendations for achieving specific STC goals. Several online resources and publications offer guidance on STC ratings and wall construction. These resources can help in understanding the principles of sound isolation and selecting appropriate materials and construction techniques. In conclusion, achieving the desired STC ratings of 45 to 49 or 50 to 56 requires careful attention to stud spacing and other elements of the wall assembly. Growing every other stud is not sufficient to meet these STC goals. Instead, closer stud spacing combined with other sound isolation measures is necessary to create walls that effectively block sound transmission. Building codes such as the International Building Code, or IBC, references construction and design requirements that cover aspects of building, including aspects such as sound transmission. Within the IBC, specific requirements and recommendations will relate to sound transmission class ratings for walls, floors, and ceilings in various occupancies. Occupancies include residential, commercial, or healthcare. The IBC goal is to protect occupants from noise. For wall assemblies, the IBC often references ASTM 90, which defines the standard test method for laboratory measurement of airborne sound transmission loss of building partitions and elements. These standards, or others, will define exactly how sound tests are performed so that products and assemblies meet the rating requirements in order to control sound transmission. The American Society for Testing and Materials, or ASTM, a 90 standard specifically outlines the procedures for measuring the airborne sound transmission loss of building elements, including walls. This standard is used to determine the STC rating of a wall assembly, as we previously discussed. The test setup involves placing a wall assembly, typically 8 feet wide and 9 feet tall, between two reverberation rooms. A sound source is generated in one room, and the sound pressure levels are measured in both rooms. The difference in sound pressure levels between the two rooms is used to calculate the sound transmission loss, which is then converted to an STC rating. The STC rating is a single number rating that represents the overall sound isolation performance of the wall assembly. A higher STC rating indicates better sound isolation. The ASTM 90 standard specifies the stud spacing for the test assembly as 16 inches on center. This spacing is used as a reference point for comparing the sound isolation performance of different wall assemblies. The standard also specifies the types of materials that should be used in the test assembly, such as drywall, insulation, and framing members. Achieving a specific STC rating involves carefully selecting materials and construction techniques that optimize sound isolation. Stud spacing is one important factor to consider, but other factors, such as the type and thickness of drywall, the use of resilient channels, and the presence of insulation also play a significant role. Going back to the IBC, it is important to check your local jurisdictions because requirements and enforcement might be different depending on the specific codes adopted and how they are enforced locally. The IBC serves as a model code, and local jurisdictions may adopt it in whole or in part, or they may develop their own building codes. Because of the customization of the IBC at a local level, it's important to consult with local building officials or qualified professionals, such as architects or engineers, to ensure compliance with the specific requirements in your area. So while the IBC and ASTM 90 provide valuable guidance on STC ratings and wall construction, it's important to remember that local building codes and regulations may have additional or different requirements. Therefore, it's essential to consult with local authorities and qualified professionals to ensure compliance. When specifying STC requirements, it's important to consider the specific needs of the application. For example, in residential buildings, STC ratings of 45 to 50 may be sufficient to provide adequate sound isolation between living spaces. However, in commercial buildings, such as offices or hotels, higher STC ratings may be required to minimize noise transmission between different areas. In healthcare facilities, even higher STC ratings may be necessary to protect patient privacy and create a quiet and healing environment. To ensure that wall assemblies meet the required STC ratings, it's important to conduct thorough testing and inspection. This may involve laboratory testing of wall assemblies according to ASTM 90, as well as field testing of installed walls to verify their acoustic performance. Field testing can help to identify any weaknesses in a wall construction and ensure that the specified STC ratings are achieved. In addition to STC ratings, other acoustic metrics may be relevant in certain applications. For example, noise reduction coefficient, or NRC, is a measure of a material's ability to absorb sound energy. NRC is often used to evaluate the acoustic performance of ceiling tiles, wall panels, and other sound-absorbing materials. Impact Insulation Class, or IIC, is a measure of a floor-ceiling assembly's ability to isolate impact noise, such as footsteps. IIC is particularly important in multi-story buildings to minimize noise transmission between floors. When designing and constructing walls for sound isolation, it's important to consider all relevant acoustic metrics and select materials and construction techniques that optimize overall acoustic performance. This may involve using a combination of sound-blocking and sound-absorbing materials, as well as implementing careful detailing and construction practices to minimize sound leaks. In summary, achieving the desired STC ratings in wall construction requires a comprehensive approach that considers stud spacing, material selection, and construction techniques. Consulting with qualified professionals and following established standards and guidelines can help to ensure that wall assemblies meet the specific acoustic needs of the application. Remember to check and adhere to local jurisdictional requirements, as they might vary from the broader standards mentioned. Sound transmission class ratings relate to other aspects of building acoustics and design, including architectural acoustics. Architectural acoustics deals with planning, design, construction, and use of spaces to ensure the best possible sound quality. This field includes optimizing factors such as reverberation time, sound diffusion, and sound absorption to create an environment suitable for its intended use, whether it is speech, music, or simply a quiet, functional space. In architectural acoustics, the goal is to control noise and sound reflections to achieve clarity and intelligibility while minimizing unwanted echoes and reverberation. In contrast, noise control is a separate but related field that aims to reduce or eliminate unwanted sound. This can involve using barriers, sound-absorbing materials, and other techniques to block or absorb sound energy. Noise control is often used in industrial settings, transportation systems, and residential areas to protect people from excessive noise exposure. An acoustical consultant is a professional who specializes in the science of sound and vibration. Acoustical consultants provide a range of services, including noise assessments, sound isolation design, and vibration analysis. They work with architects, engineers, and building owners to develop solutions that meet specific acoustic requirements. When designing for sound isolation, it's important to consider the entire building envelope, including walls, floors, ceilings, windows, and doors. Each of these elements can contribute to sound transmission, and it's important to address any weaknesses in the design. For example, windows and doors are often a weak point in sound isolation, so it's important to use high-quality, sound-rated products. When selecting materials for sound isolation, it's important to consider their mass, stiffness, and damping properties. Materials with high mass and stiffness, such as concrete and steel, are effective at blocking sound transmission. Materials with high damping properties, such as rubber and viscoelastic polymers, are effective at absorbing sound energy. In addition to material selection, construction details also play a critical role in sound isolation. For example, it's important to seal any gaps or cracks in the construction to prevent sound leaks. It's also important to isolate mechanical equipment such as HVAC systems to prevent vibration and noise from being transmitted through the building structure. When designing for sound isolation, it's important to consider the frequency range of the sound being isolated. Different materials and construction techniques are effective at different frequencies. For example, low-frequency sound is more difficult to isolate than high-frequency sound, so it may be necessary to use more massive materials or more complex construction techniques. In some cases, it may be necessary to use active noise control systems to reduce noise levels. Active noise control systems use microphones and loudspeakers to generate sound waves that cancel out unwanted noise. These systems are often used in industrial settings and transportation systems to reduce noise exposure. Sound masking is another technique that can be used to improve speech privacy in open-plan offices and other spaces. Sound masking systems generate a background sound that covers up speech sounds, making it more difficult to understand conversations. This can help to reduce distractions and improve productivity. In addition to designing for sound isolation, it's also important to consider the acoustic environment within a space. Reverberation time is a measure of how long it takes for sound to decay in a space. A longer reverberation time can make it difficult to understand speech and can create a sense of echo. Shortening the reverberation time can improve speech intelligibility and create a more comfortable acoustic environment. Sound absorption is the process of converting sound energy into heat. Sound-absorbing materials such as acoustic panels and carpets can be used to reduce reverberation time and improve the acoustic environment in a space. Sound diffusion is the process of scattering sound waves in different directions. Sound-diffusing materials, such as textured walls and ceilings, can be used to create a more uniform sound field and reduce the occurrence of echoes. When designing for acoustics, it's important to consider the specific needs of the space. For example, a concert hall will have different acoustic requirements than an office building. It's also important to consider the budget and the aesthetic requirements of the project. In summary, architectural acoustics is a complex and multifaceted field that involves optimizing the sound environment in a space. By considering factors such as reverberation time, sound absorption, and sound diffusion, it's possible to create spaces that are both functional and aesthetically pleasing. When combined with sound isolation techniques, it's possible to create buildings that provide a comfortable and productive environment for occupants. Remember to consult with qualified professionals and follow established standards and guidelines to ensure that your project meets the specific acoustic requirements. When referring to stud spacing, the term on-center or OC is commonly used. Stud spacing refers to the distance between the center of one stud to the center of the adjacent stud. The distance is measured along the length of the wall or framing member. Typical stud spacing is 12 inches, 16 inches, or 24 inches on center. The stud spacing is determined by the load-bearing requirements of the wall or framing member, as well as the type of sheathing or cladding that will be applied to the exterior. Closer stud spacing results in a stronger and more rigid wall. When constructing walls for sound isolation, it's important to consider the stud spacing. Closer stud spacing can help to reduce sound transmission through the wall. However, closer stud spacing can also increase the cost of construction. In addition to stud spacing, the type of stud used can also affect sound transmission. Wood studs are generally more effective at reducing sound transmission than metal studs. However, metal studs are more resistant to fire and moisture. When constructing walls for sound isolation, it's important to use a combination of wood and metal studs to achieve the desired level of performance. The International Building Code, or IC, provides specific requirements for stud spacing and other aspects of wall construction. The IBC is a model code that is adopted by many state and local jurisdictions in the United States. When designing and constructing walls, it's important to comply with the requirements of the IBC. The American Society for Testing and Materials, or ASTM, publishes standards for testing and evaluating the performance of building materials. ASTM 90 is a standard test method for measuring the sound transmission loss of building partitions and elements. This test method is used to determine the sound transmission class, or STC, rating of a wall assembly. When selecting materials for wall construction, it's important to consider their STC rating. The STC rating is a measure of how well a material blocks sound transmission. A higher STC rating indicates better sound isolation performance. In addition to the STC rating, it's also important to consider the noise reduction coefficient, or NRC, of a material. The NRC is a measure of how well a material absorbs sound energy. Materials with high NRC values are effective at reducing reverberation and echo in a space. When designing and constructing walls for sound isolation, it's important to use a combination of materials with high STC and NRC ratings. This will help to create a space that is both quiet and comfortable. In summary, stud spacing is an important factor to consider when constructing walls for sound isolation. Closer stud spacing can help to reduce sound transmission through the wall. However, it's also important to consider the type of studs used and the requirements of the International Building Code. By using a combination of materials with high STC and NRC ratings, it's possible to create spaces that are both quiet and comfortable. And again, remember local jurisdictions and their various building codes that might customize or alter the IBC. Understanding and adhering to those local codes will be of the utmost importance. When working with electrical systems in the context of building construction and sound isolation, it's also necessary to consider electrical safety. While electrical systems are not directly related to STC ratings, their installation and placement can impact the overall sound isolation performance of a wall or building assembly. Electrical boxes, wiring, and conduits can create pathways for sound to travel through a wall, reducing its STC rating. Therefore, proper installation techniques and materials are essential to maintain the desired sound isolation. National Electrical Code, or NEC, addresses the safe installation of electrical wiring and equipment. While the NEC does not specifically address sound isolation, its requirements for ceiling penetrations and maintaining fire stopping can contribute to reducing sound transmission. The NEC covers various aspects of electrical installations, including wiring methods, overcurrent protection, grounding, and equipment installation. Compliance with the NEC is essential to ensure the safety of occupants and prevent electrical hazards. When installing electrical boxes in walls that require sound isolation, it's important to use putty pads or other sound deadening materials to seal around the box and prevent sound from traveling through the wall cavity. These materials help to fill any gaps or cracks around the electrical box, creating a barrier that reduces sound transmission. It's also important to use low-noise electrical devices, such as dimmers and switches, to minimize the amount of noise generated by the electrical system. Some electrical devices can produce audible noise that can be transmitted through the wall, reducing its STC rating. When running electrical wiring through walls that require sound isolation, it's important to use flexible conduit or other sound deadening materials to dampen vibrations and prevent sound from traveling along the wiring. These materials help to isolate the wiring from the wall structure, reducing the amount of sound that is transmitted. It's also important to avoid running wiring through studs or other framing members, as this can create a pathway for sound to travel through the wall. When installing lighting fixtures in ceilings that require sound isolation, it's important to use recessed fixtures with airtight seals to prevent sound from traveling through the ceiling cavity. These fixtures help to create a barrier that reduces sound transmission. It's also important to use low-noise ballast or LED drivers to minimize the amount of noise generated by the lighting system. When selecting electrical equipment for use in buildings that require sound isolation, it's important to consider the noise levels produced by the equipment. HVAC systems, transformers, and other electrical equipment can generate significant amounts of noise that can be transmitted through the building structure. Therefore, it's important to select equipment that is designed to minimize noise levels. When designing electrical systems for buildings that require sound isolation, it's important to coordinate with the architect and acoustical consultant to ensure that the electrical system is compatible with the overall sound isolation design. This coordination can help to identify potential problems and ensure that the electrical system does not compromise the sound isolation performance of the building. In summary, electrical systems can impact the sound isolation performance of a wall or building assembly. By following proper installation techniques, using sound deadening materials, and selecting low-noise electrical equipment, it's possible to minimize the amount of noise transmitted through the electrical system and maintain the desired STC rating. Compliance with the National Electrical Code, or NEC, is essential to ensure the safety of occupants and prevent electrical hazards. Therefore, it's important to consult with qualified electrical contractors and engineers to ensure that electrical systems are designed and installed in accordance with all applicable codes and standards. When integrating fire safety measures into wall assemblies designed for sound isolation, it's crucial to maintain the fire resistance rating of the wall while also ensuring that sound transmission is minimized. Fire resistance ratings, typically expressed in IROs, indicate the amount of time a wall assembly can withstand exposure to fire before structural failure or fire spread occurs. Maintaining this rating is paramount to protect occupants and prevent the spread of fire. Fire-stopping materials are used to seal penetrations in walls and floors, preventing the passage of fire and smoke. These materials are designed to expand when exposed to heat, effectively blocking the opening and maintaining the fire resistance rating of the assembly. When installing fire-stopping materials in walls that require sound isolation, it's important to select products that also have good sound deadening properties. Some fire-stopping materials can actually increase sound transmission, so it's important to choose products that minimize this effect. Fire-rated electrical boxes are designed to maintain the fire resistance rating of a wall assembly when electrical boxes are installed. These boxes are typically made of metal and are designed to prevent the spread of fire and smoke through the wall cavity. When installing fire-rated electrical boxes in walls that require sound isolation, it's important to use putty pads or other sound-deadening materials to seal around the box and prevent sound from traveling through the wall. Fire-rated insulation is designed to provide thermal insulation and fire protection. Some types of fire-rated insulation also have good sound-deadening properties. When selecting insulation for walls that require sound isolation, it's important to consider both the fire resistance rating and the sound deadening properties of the insulation. Fire-rated drywall is designed to provide fire protection and is typically used in walls and ceilings that require a fire resistance rating. Fire-rated drywall is typically thicker and denser than standard drywall, which can also improve its sound deadening properties. When constructing walls that require both fire protection and sound isolation, it's important to use fire-rated drywall in conjunction with other sound-deadening materials. Fire dampers are used in HVAC systems to prevent the spread of fire and smoke through ductwork. Fire dampers are typically installed in walls and ceilings that have a fire resistance rating. When installing fire dampers in HVAC systems that serve areas that require sound isolation, it's important to select dampers that are designed to minimize noise transmission. Fire-rated doors and windows are designed to provide fire protection and are typically used in walls that have a fire resistance rating. When selecting fire-rated doors and windows for buildings that require sound isolation, it's important to choose products that also have good sound deadening properties. In summary, integrating fire safety measures into wall assemblies designed for sound isolation requires careful consideration of the fire resistance rating of the wall and the sound deadening properties of the materials used. By selecting fire-rated materials that also have good sound deadening properties, it's possible to create walls that provide both fire protection and sound isolation. Therefore, it's important to consult with qualified fire protection engineers and acoustical consultants to ensure that wall assemblies are designed and constructed in accordance with all applicable codes and standards. When dealing with plumbing systems in building construction and considering sound isolation, it's important to recognize that plumbing can be a significant source of noise transmission. Water flowing through pipes, the operation of plumbing fixtures, and the sound of pumps can all contribute to noise levels within a building. Therefore, proper design and installation techniques are essential to minimize plumbing noise and maintain the desired sound isolation. Decoupling pipes from the building structure can significantly reduce the transmission of vibrations and noise. This can be achieved by using resilient hangers or isolation clamps to support pipes, preventing direct contact between the pipes and the studs, joists, or other structural elements. Wrapping pipes with sound-deadening materials, such as pipe insulation or acoustic legging, can help to absorb vibrations and reduce noise transmission. These materials act as a barrier, preventing the pipe from radiating noise into the surrounding space. Installing noise-dampening plumbing fixtures such as low-flow toilets and quiet operation faucets can help to minimize the amount of noise generated by the plumbing system. These fixtures are designed to operate more quietly than standard fixtures, reducing the overall noise level. Locating plumbing away from noise-sensitive areas such as bedrooms, offices, and meeting rooms can help to minimize the impact of plumbing noise on these spaces. This can be achieved by carefully planning the layout of the plumbing system and avoiding running pipes through or adjacent to these areas. Using vibration isolation pads under pumps and other mechanical equipment can help to reduce the transmission of vibrations and noise into the building structure. These pads act as a cushion, absorbing vibrations and preventing them from being transmitted to the surrounding surfaces. Adding master pipes can help to reduce vibrations and noise transmission. This can be achieved by using heavier gauge pipes or by wrapping pipes with mass-loaded vinyl. This added mass helps to dampen vibrations and reduce the amount of noise radiated by the pipes. Installing sound barriers around plumbing equipment, such as pumps and water heaters, can help to contain noise and prevent it from spreading to other areas of the building. These barriers can be constructed of sound-deadening materials, such as mass-loaded vinyl or acoustic panels. In summary, plumbing systems can be a significant source of noise transmission in buildings. By following proper design and installation techniques, it's possible to minimize plumbing noise and maintain the desired sound isolation. The first important aspect is decoupling pipes from the building structure. Secondly, wrapping pipes with sound-deadening materials. Thirdly, installing noise-dampening plumbing fixtures. Fourthly, locating plumbing away from noise-sensitive areas. Fifthly, using vibration isolation pads under pumps and other mechanical equipment. Sixthly, adding master pipes. And lastly, installing sound barriers around plumbing equipment. It is important to consult with qualified plumbing engineers and acoustical consultants to ensure that plumbing systems are designed and installed in accordance with all applicable codes and standards, taking into account the specific sound isolation requirements of the building.